Okay, today we're going to take a look at vectors and vector functions. If we have some quantity that gives us magnitude or the amount, but it doesn't specify a direction, we call it a scalar. Time, temperature, and speed are all scalars. Remember that speed tells us how fast we're going, but it's always positive. It does not indicate which direction we're going. If we have a quantity that gives us the direction as well as magnitude, we call it a vector. And we can represent vectors as directed line segments. So they have a beginning and an ending, as well as an arrow to indicate which way they're going. So compare speed to velocity. Velocity can be positive and negative because velocity not only tells us how fast we're going, but which direction we're going. So velocity would be represented by a vector. Here we have a vector from A to B. So we call A the initial point, B is the terminal point. And the notation we can use is AB with this little arrow over the top to indicate that it's a vector. We can show the magnitude or the length of the vector by putting absolute value bars around it. Keep in mind that absolute value means the distance from 0 or the length. So when we use these absolute value bars for magnitude, that's exactly what we're saying, is the length of the vector AB. And it's important to understand that vectors are considered to be equal if they have the same length and same direction, or the same slope, regardless of where they actually are in space. So we can have two vectors with the exact same length, pointing up at the exact same angle, and they're both considered to be equivalent. Here we have a vector in standard position. So if vectors are equal despite where they are in space, we can take that vector and move it down so that the initial point is at the origin. And that's our standard position for a vector. Our component form, this is how we typically write a vector. We use these angled brackets, which are called chevrons, to indicate that we're talking about a vector. So the vector v has coordinates of the endpoint of v sub 1 and v sub 2, starting at the origin. And here's just a really quick notation thing you guys should be aware of. If we are typing and indicating we have a vector, we use boldface. So you can see a boldface V or a boldface U represent vectors. But if you're writing, it's cumbersome to actually have to write something in boldface, so that's where we use the arrow over the top. So V and U, both with an arrow over the top, also represent vectors. So different notations whether we're typing or writing. So in my notes, you'll typically see boldface V. As you're writing things down, you should be using a V with an arrow over the top to represent the same thing. If you want to find the magnitude of a vector, you can think of how we could use the Pythagorean theorem. Take the square of the x distance, the square of the y distance, add them together, and take the square root. So here's a vector PQ, and you can see it's not in standard position. So if we want to turn this into component form, we take head minus tail, so -5 minus -3 for the x components, 2 minus 4 for the components, and we find that that vector v is in component form -2, -2. So this vector can start at the origin, go left 2, down 2, and you can see it has the same length and the exact same angle as the vector PQ, but now it's in standard position. And we can find the length by taking the square root of the sum of the squares, so that has a length of root 8, or 2 root 2. If the magnitude of the vector equals 1, we call the vector a unit vector, meaning it has a length of 1 unit. The vector 0, 0 is the 0 vector, has no direction and no magnitude. All right, when we have vectors, we're going to need to be able to add, subtract, multiply by a constant, and so we're going to take a quick look at how all of that works. If we have two vectors, u and v, and k is a scalar, meaning it's just a numerical value, doesn't have any direction, we can add the two vectors u plus v by adding their components. We can subtract u minus v by subtracting their components, so we subtract the x values, we subtract the y values to come up with the new vector u minus v. Multiplying by a scalar, so if we take a number and we multiply it by our vector u, we just multiply that number by each of the components. If we're multiplying by a negative, or if we have the negative vector, we're multiplying by -1, so we multiply each component by -1. Now here's where vectors can be really useful for us. We can use vectors to describe motion in space. So you can see this curve here. We could think of this curve as being described by the head or the endpoint of a vector function. So that vector, we'll call it r of t, is equal to some function x of t and some function y of t. Those describe the components of the vector. As we plug in different values of t, that arrow is going to point to different places in space. And we think of the head of the arrow as just tracing out that curve. So really what we have here are parametric equations, but we're describing them now in terms of a vector. So we put the x equation as the x component in the vector, the y equation is the y component in the vector. All right, on a TI Nspire, on our calculator, we can graph these. And like we just said, we're essentially dealing with parametric equations. So if we're trying to graph the vector function t cosine of t, t sine of t, we're just graphing the parametric equations t cosine of t, t sine of t. So keep in mind, when we're graphing a vector function, we're not actually graphing a single vector. It's a collection of all of the points traced out by the ends of the vectors. And we end up with this spirally graph. If you want to see more of it, you can zoom out. So if we're given a position vector here, 3 cosine of t, 3 sine of t, we want to find the velocity and acceleration vectors. And to do so, we just take the derivatives. First derivative for velocity, second derivative for acceleration, and we take the derivative component by component. So derivative of the x component, derivative of the y component to find the velocity vector. The acceleration vector is the second derivative of both the x and y components. And now we want to find position, velocity, acceleration, and speed at the time t equals pi over 4. So position, using the original equation, plug in pi over 4 for t, and we find that the position vector gives us 3 over root 2, 3 over root 2. To find the velocity vector, plug pi over 4 into the velocity vector function, and simplify. And to find acceleration, plug pi over 4 into the acceleration vector. So now we have our vectors for position, velocity, and acceleration, which just leaves us with speed. To find speed, we find the magnitude of velocity. So we take the square root of the sum of the squares, which turns out to be 3. So recall that position, velocity, acceleration are all vectors, but speed is a scalar, which is why it's just a single value. Okay, here's another position equation. We want to find the equation of the tangent when t equals -1. So we can find the velocity, that's our derivative. At t equals -1, our position is -5, 11. Our velocity is 12, -9. So we have our position at that point. Recall that the vector points to the position, so the vector points to the point -5, 11. Our velocity vector points to 12, -9, which means it has a slope of -3/4, because velocity is the derivative, derivative represents slope. So the tangent line, using our point slope equation, plug in all those values, and there's the equation of the line tangent to the vector function given. Here's the curve graphed on the calculator. And there's the equation of that tangent line. You can see it clearly is tangent right there in that quadrant 2. We want to find anywhere on the path where the horizontal component of the velocity is 0. The horizontal component is given by the x value. That's where we move left and right. So we let the x value equal 0, divide by 6, factor, and solve. So at t equals 0 and t equals 1. So our position at t equals 0 is 0, 0. And our position at t equals 1 is -1, -11. If we look back at the graph right here, and we plot those points, you can pretty clearly see that that's where this graph changes direction from moving left to right or right to left.